Hi, this is Yujia Huang from Caltech. Today I'm going to talk about learning efficiently with biologically inspired feedback. So here's the outline of today's talk. I'll motivate the feedback mechanism by the gap between artificial neural networks and human visual performance. I'll also show some neuroscience findings about the existence of feedback connections in the brain. Then I'll introduce the classical computational neuroscience model, which is the predictive coding theory that provides a principled model for feedback mechanism. Moving on, I'll introduce some recent works in building feedbacks into modern deep learning models, and also our work in incorporating recurrent generative feedback into neural networks. I'll conclude the talk with some takeaway messages and thoughts on future works. Okay, let's get started. So as we all know, human can learn from very few data points. Given a few images from the support dataset, human can correctly classify images in the query dataset. Humans are also robust, while artificial neural networks tend to fail when facing unseen corruptions during test time. This is crucial for safety deployment of AI because by no means can we cover all the variations in the training dataset. In addition, humans are robust to adversarial attacks, while artificial neural networks can be fooled by adversarial images. So for instance, an artificial neural network would classify a panda as a gibbon when small and semantically meaningless noise is added to the original image. So the mismatch between artificial neural networks and human visual performance indicate that there is a missing part in the artificial neural networks. Some cognitive science and neuroscience experiments give some clues about the missing parts. In this experiment, the authors show that humans can actually also be fooled by adversarial images under limited time. For instance, 67% of the participants wrongly classified this spider image as a snake when it is being presented very briefly. And when it is being showed long enough, all the people correctly classified the image. Another work shows that it takes longer to recognize the core object in challenging images. The researchers have one set of challenging images and another set of control images. In the challenge images, the core objects lie in the corner and are occluded, which makes them much harder to be recognized. And here it shows that the OST time is longer for challenging images, and OST stands for Object Solution Time. These works indicated the existence of recurrent feedback in the brain, and there are computational models that have provided a principled way to describe it. One of the classical theories is predictive coding. As a disclaimer here, the term predictive coding could have more general meanings, but here we only discuss the theory that focuses on visual processing. So predictive coding was proposed to explain a phenomenon called surround suppression. The green and red ellipses represent the receptive field. When the stimulus, which are the sinusoidal gratings, enlarge, the neuron's response decreases. This was not intuitive, and predictive coding theory provides a functional explanation of this. So according to predictive coding theory, the feedback connections from a high level of visual cortical area carry predictions of lower level neuronal activities. And feed-forward connections carry the residual errors between the predictions and the actual low-level activations. The predictive estimator computes the residual errors and the prediction for the lower level by f of UR. You can think of R as causes for responses in the lower level and U as a dictionary, and F is some nonlinear function. The R can be optimized by minimizing the distance between the prediction and actual responses. And R can be updated by a gradient descent that involves U transpose and the residual errors. So this curve here shows the reduction in the level 1 residual errors. as the bar extends beyond the classical receptive field in level 1. As we can see, as the top-down prediction gets more accurate, the neuron's response decreases. So predictive coding theory successfully explained the surround suppression phenomenon. And this theory was proposed in 1999 and has greatly influenced neuroscience thinking. So besides this classical theory, there are a lot of recent works that attempt to incorporating feedback mechanisms into modern deep learning models. And they may aim for different tasks and use different modules, but the common piece is feedback. I'll give a brief overview here. So in this work, the authors performed automated search over thousands of model architectures to identify novel local recurrent cells and long-range feedback connections that are useful for object recognition. It turns out that this cell that involves bypassing and gating were able to boost task accuracy substantially. Also, this model matches the dynamics of neural activity in the primate visual system better than feed-forward networks. In this work, the authors propose an architecture called CoreNet-S. CoreNet stands for Core Object Recognition. And CoreNet is artificial neural networks, very shallow. It only has 4 anatomically mapped areas as V1, V2, V4, and IT in the brain. Each area is modeled with a block with recurrent connectivity. Despite being significantly shallower than most deep learning models, this model is the top model on BrainScore and has reasonably high classification accuracy on ImageNet. Moreover, the ablation study on CoreNet-S circuitry shows that recurrence is the main predictive factor of BrainScore. You may ask, what is BrainScore? BrainScore is a large-scale benchmark to quantify the functional similarity between artificial neural networks and the primate ventral visual system. Despite the success of these architectures in modeling neuronal activities, we still want a principled and interpretable way to incorporate feedback into artificial neural networks. And one attempt is to use probabilistic modeling. This model, recursive cortical network, RCN, is a probabilistic generative model for vision. So an image is generated hierarchically from contours to surface. And there are also lateral connections between subnetworks. And here's an example of a 3-level RCN representing the contours of a square. So features at level 2 represents the 4 corners, and each corner is represented as a conjunction of 4 line segment features. And here's a more complicated example where a 4-level networks representing a letter A. So here's the inference procedure in RCN. Images are first preprocessed by a bank of Gabor-like filters to extract the edges. And in the feed-forward pass, some hypothesis will be produced about the multiple letters presented in the input image. And then in the backward pass, the segmentation mask will be created for a selected feed-forward pass hypothesis. So for example, here, the mask of the letter A will be produced in the feedback pass based on the hypothesis A in the feed-forward guess. Also, there could be hallucinated letters from false hypotheses. For example, V here is hallucinated at the intersection of letter A and K. And of course, multiple hypotheses can be activated to produce a joint explanation. In this case, A and O are extracted. The authors tested the effectiveness of RCN on CAPTCHA dataset. So CAPTCHA datasets are images that are used by websites to block automated interactions. And this is a problem that is easy for human beings but difficult for computers. Here it shows the top 2 segmentation and parsing solutions from RCN and human labels from 2 different people. We can see that the RCN can successfully segment and parse the capture images. Also, when the character spacing is changed between the testing set and the training set, RCN is much more robust than CNN. And here the authors shows the effectiveness of each design component in RCN. So with both feed-forward and feedback connections and also lateral connections, RCN can learn from much fewer training data points to classify than without these design components. So besides probabilistic modeling, a recent work proposes to combine top-down and bottom-up signals via attention mechanism. The hypothesis is that bottom-up signals focus more on the details, while top-down signals focus more on the relevant context and background knowledge. So imagine you enter a dark room and want to do some navigation. So without seeing the room clearly, you may depend more on the top-down signals because that contains your prior information or knowledge about this room. If you turn the light on, you might depend more on the bottom-up signals because you can see the details of the room clearly and you can rely on your input. So properly combining these top-down and bottom-up signals can lead to better generalization. And here shows the proposed architecture in this paper. There's a 2-layer network with 3 modules in each layer. The red arrows show bidirectional connections to provide top-down information. The dark blue box shows the activated modules, and the light blue box shows the deactivated modules. The green arrows stands for communications within each layer. Here's a very interesting experiment to verify the hypothesis we just discussed. So the authors injected noise in the images. As the amount of noise increases, we can see that the model relies more on top-down feedback. So this aligns with the hypothesis that top-down modulation should be queried more when there is more uncertainty. Okay, now we move on to our work in introducing recurrent generative feedback into neural networks. So we combine modern convolutional neural networks, CNNs, with Bayesian inference. This is a joint work with James Gornet, Sihui Dai, Zhiding Yu, Tan Yuan, Doris Cao, and Arnima Anandkumar. So the essential idea of our work is to use an internal generative model to update the posterior beliefs of the sensory input. Okay, so imagine you see a blurry cat. First, the image will undergo some pre-processing. You would have some preliminary idea about what the image is, so it's probably a cat. Then you try to generate a cat from the internal model given the label and some latent variables. So these latent variables can be some detailed aspects of the image. So if the generated image roughly matches with the input stimulus, that will confirm your first guess. Otherwise, you may need to refine the first guess. And this process can happen recurrently until you have reached a consistent solution for the content of the image. And we formulate this by what we call self-consistency requirements. So we use X to denote images, H to denote encoded features of the images, Z to denote latent variables, and Y to denote the labels. Given a joint distribution on H, Y, and Z parameterized by theta, we call the map. By map, we mean maximum a posterior estimate. H hat, Y hat, and Z hat are self-consistent if they satisfy the following constraints. So for each input instance, the model should reach a self-consistent solution. And the arrows of different color here stands for each of these 3 map estimates. So here we use the cat image as a demonstration again. The latent variables could be the color and size of the cat, the lightening of the image, or the background of the image. Given the joint distribution of the image, latent variables, and labels, you should be able to infer one component from the other 2. Also, the self-consistent solution from the internal model should roughly align with the external stimuli. With this definition, an adversarial image and its wrong label is not self-consistent if our internal model is trustworthy. The reason that we, human beings, wouldn't classify this panda image as a gibbon is because we know what a gibbon looks like from our internal model, and the external stimulus just does not match our internal representation, so we cannot be fooled. With self-consistency defined, we move on to introduce the generative model that we use to describe the joint distribution. Before that, we first introduce the concept of a generative classifier. So as we all know, to learn a classifier, we can directly learn from the mapping from x to y, or p of y given x from the input data. But there is also another way. That is, we learn the joint distribution of x and y and compute p of y given x using Bayes' rule. So this is called a generative classifier. For example, logistic regression and Gaussian naive classifier is a discriminative and generative pair of classifiers that have the same parameterized form. So since SNNs have achieved great success in image classification, we hope to have a generative model whose inference has the same architecture as CNN. And it turns out that a recently proposed model called deconvolutional generative model satisfies this requirement. In the DGM, an image is generated hierarchically from coarse to fine details. First, Y is sampled from the label distribution, and features at the lower level, denoted by G here, is generated by deconvolutional operations. The latent variables are sampled from a Bernoulli distribution parameterized by the bias parameter B and generated feature map G. Notice that the latent variables are discrete and have the same dimension as G, and I here denotes the index of each entry. So the same generation process is repeated layer by layer. In the end, we assume that the image X has a Gaussian distribution centered at the generated image in the bottom layer. So we use G0 to denote the generated image at the bottom layer. And we can compute P of Y given X and Z from the joint distribution. So we need to compute the map inference for Y, H, and Z to enforce self-consistency. So with the DGM model, we can show that the map estimates can be computed via feed-forward and backward pass in a CNN architecture. The map estimate of Y can be carried out by a CNN, and the map estimate for the image features H is the generated image at the bottom level of the DGM model. And the map estimate of Z can be determined by the nonlinear operators add-a-relu and add-a-pool. And let's see how this works in detail. An image is first encoded and then passed to a convolutional neural network. After convolution, we use add-a-relu and add-a-pool to decide which feature to activate. So add-a-relu and add-a-pool change the relu and max pool units in the feed-forward pathway based on both feed-forward and feedback signals. So if the sign of the feed-forward and feedback features are the same, we let the values pass through and assign 1 to the map estimate of Z. Add-a-pool is defined in a similar way as add-a-relu. Then, after a linear layer, we can have the logits. In the feedback path, the weights are tied with the feed-forward path. We use matrix transpose and deconvolutional operations. For adaptive layers, we perform element-wise multiplication between generated feature and map estimate of Z. A dot in a circle stands for element-wise multiplication. So yeah, this slide may be a bit technical, but the main thing to keep in mind is that the inference in a DGM model can be computed via feed-forward and feedback passes in a CNN-like architecture. So zooming out from these technical details, we need to find the self-consistent solution. So we perform this iterative inference procedure. The first feed-forward pass is the same as conventional CNNs, and we initialize latent variables by the status of the normal ReLU operators. And we will have the first guess of label Y. Then we generate image features through the feedback pathway using Y and Z and feed the generated feature H to the next iteration. Here, we compute map estimate of Z using both feed-forward and feedback signals. We repeat this process until it converges to a solution empirically. And here shows the unrolled version of the iterative inference procedure, and we term this model as SNNF, which is the short for CNN with feedback. So the losses used to train SNNF are discriminative loss and generative losses. The discriminative loss is the conventional cross-entropy loss between logits and ground truth labels. And the main generative loss is reconstruction loss between generated image feature and input feature. We use subscript here to denote the number of iterations, and the losses are added to all the iterations. SNNF is also compatible with adversarial training. There are multiple ways that we can combine SNNF with adversarial training. So one way is to directly apply adversarial training on SNNF, which means that all the losses are added on adversarial images. So notice that the reconstruction loss is always between adversarial and natural features. This means that we still need to pass the natural images to an encoder to get encoded features, although we do not add any losses on those natural images. However, directly apply this adversarial training on SNNF may not be the optimal way, since we hope the generative feedback can learn how to project the adversarial features to the clean manifold. And this is very hard when the model is only trained on adversarial images. So instead, we can have cross-entropy loss on both natural and adversarial images in the first feed-forward pass to provide a good reference for natural features, and just have losses on adversarial samples in the subsequent iterations. And of course, another way would be to treat adversarial images as augmented data and have all the losses on both natural and adversarial images. Also, SNNF can be deployed to various CNN architectures, such as VGG, ORConv, and ResNet. So if there are skipping connections in the feed-forward path of ResNet, we also add corresponding skipping connections in the backward path, and the weights are tight. Okay, finishing model description, let's see some results. As a sanity check, we show that SNNF can repair distorted images. So this means that the generative feedback is working in the way that we have expected, that is to project distorted images to a clean domain where it is easier to reach the self-consistent solution. And here we show that SNNF can improve adversarial robustness. This is an experiment using standard training on FashionMNIST. We attack the model with a projected gradient descent with 40 steps. And we can see that a SNNF trained with 5 iterations outperform CNN. So epsilon here stands for perturbation magnitude in L infinity norm. And more interestingly, we find that more iterations are needed for images that have larger perturbation magnitude. And this corresponds to the neuroscience findings that I showed in the beginning of the talk. Longer processing time is needed for challenging images. And here we show when combined with adversarial training, SNNF can achieve good performance in both clean and adversarial data compared to its CNN counterparts. So here we show that SNNF generalizes better to different attacks. So we train a SNNF and a CNN with fast gradient sign method adversaries, FGSM adversaries, and attack with a much more effective method, PGD40. And we can see that CNN is vulnerable, while SNNF can maintain some robustness. Also, SNNF has higher accuracy for adversarial attack with different perturbation magnitudes, while CNN suffers from drastic accuracy drop when increasing the perturbation magnitude. So this indicates that feedback helps when there is a distribution shift between training and test data. We also tested CNNF on wide ResNet architecture on CFAR10, and here we show the result of conventional adversarial training and CNNF trained with partial augmentation with adversarial data. And this figure shows the accuracy over a number of iterations. We can see that for clean images, the first feed-forward pass already give good enough performance, and there is no need for overprocessing, while for adversarial images, more iterations are needed. Okay, time to wrap up. In this talk, I mainly discussed biologically inspired recurrent feedback and show how it can help the model to learn with less data and generalize better to unseen variations in the test dataset. And there are, of course, other biologically inspired components that could be crucial to reduce the gap between artificial neural networks and human visual performance. These mechanisms could be lateral connections and sparsity. In fact, the feedback idea I discussed today also has close relationship with other fields such as signal processing and control. Also, as a general principle, the feedback mechanism could be deployed to multiple downstreaming tasks such as robustness, few-shot learning, uncertainty quantification, etc. So I encourage all of us to think out of the box and bring some new pieces to the computer vision community. And thanks a lot for listening. If you have questions or thoughts, please don't hesitate to email me or attend the live Q&A session. Thanks.